Good evening, everyone. I'd like to warmly welcome you to another instalment of the Enlightening Minds series, our last for the academic year, where our aim is to inspire and nurture curiosity across the whole of the King's community. Thank you very much for joining us either in person or online via the live stream. I do have a bit of practical business before we begin. We don't have a fire drill scheduled, but in the very unlikely event of a fire, please follow my lovely stewards over here and assemble on the first 15 pitch, which is just outside. We're delighted to put on these intellectually inspiring talks free of charge to the King's community. Thank you to those who donated to the school's bursary fund when you booked your ticket. But if you haven't already done so, please do consider doing this retrospectively by the King's community page of the school website. There will be a Q&A at the end of the talk, and those who are watching online can ask a question using the hashtag KCS Enlightening Minds on X. Lovely. Thank you. Over to the sixth form.
Hello. Dr. Aaron LeBlanc is a paleontologist who earned both his bachelor's and master's at the University of Alberta, Canada, and his PhD at the University of Toronto. However, he has a fascination with the evolution and development of teeth for many, many years and in many organisms, from fish to mammals to even prehistoric reptiles. His expertise focuses on the interpretation and imaging of fossilized teeth and the relationship between dentistry in the prehistoric times and dentistry in the present to understand how the structure of our teeth has developed over the last 20 million years. In previous research, he has investigated the evolutionary origins of periodontal tissue, which are gums, and dental adaptations to herbivory in extinct reptiles, and he is now a lecturer at King's College University since September 2020. Without further ado, ladies and gentlemen, Dr. Aaron LeBlanc.
All right, well, first order of business, can you all hear me okay? Great, great, and thank you for the lovely introduction. That is probably the best introduction I've ever had, so thank you. And thank you as well to the organizers of this for inviting me, because I'm always happy to come and talk to the wider community about the things that we do in my lab, and a little bit about the quirky history of my own personal and professional life so far. So I have made 3 promises in this talk to talk about dinosaurs, dentists, and dragons. And so I'm going to try and take you through this for the next little while and explain what these things might possibly have in common. But first, as the introduction alluded to, and as you probably got from my accent, I'm not from anywhere around here. I'm from Canada. I'm from Western Canada, the western province of Alberta, from the capital city of Edmonton. Very, very cold in the winter, very, very dry. And I grew up with a childhood fascination with dinosaurs and all things extinct. And I think there are probably a few people here today that would say they're in the same boat, right? And I don't know why, but I was absolutely obsessed with them. And of course, would read about them and watch shows about them, and just wanted to learn more about them. And I also grew up in an area that was going to just keep promoting that, because that part of Western Canada has a really, really rich fossil record. And there's some really amazing sites there, especially of Cretaceous dinosaurs. So that's towards the end of the reign of the dinosaurs that you can go to. So this, I was told, is a picture of me as I'm 6 years old, still with my impeccable fashion sense. And my mom took this photo in a place called Drumheller. And I would make this pilgrimage every summer to go there, to go to the museum that they have there, which is absolutely world-class, the Royal Tyrrell Museum, which has all these dinosaurs and other things to look at. And so I'd go there all the time, so that didn't help to shed this obsession with all things fossil. And as in the introduction you just mentioned, the University of Alberta, which is in my hometown, also has one of the best paleo programs I've ever seen. I mean, I'm a little biased. And so it helped me foster my academic interest in paleontology. So I did a bachelor's and a master's degree there and really cut my teeth, no pun intended, learning how to study fossils professionally. And from there, and I'm going to come back to this picture and why I chose this picture, I actually came here in October 2020. And I think everyone remembers what October 2020 was like. Not a great time to move across the Atlantic Ocean, but we did it, and we're glad we did. Again, I'll explain this picture in a little bit. So I started out with an undergraduate degree and then the master's degree at the University of Alberta, where I got to learn how to be a professional paleontologist for the first time. And one of the first things I got to work with was not a dinosaur. In fact, I very quickly realized I actually prefer these types of animals instead. This is something called a mosasaur. It's a giant marine lizard from the late Cretaceous period. So they would have lasted right up till the time of Tyrannosaurus rex, 66 million years ago. And you find their fossil remains from marine rocks that go all over the world. You find them in Antarctica, you find them in Africa, you find them in North America, you find them in Europe. So they were very widespread, very successful. This particular one was from Morocco, from Northern Africa, and I got to study it and even give it a name. So I got to name a new species to science from Morocco. This is what they looked like. So they were fully marine animals, so they spent their whole life out in the open ocean, gave birth to live young out there. They ate fish and all kinds of other things, depending on how big they were. You've probably seen them in Jurassic World. Who here has seen Jurassic World? Yeah, there we go. Okay. So the big thing that comes out of the water and eats the shark, it's a bit too big. So typically a giant mosasaur would be up on the order of about 10 meters long, so still quite large. This one's not quite that big, but here's a graduate student for scale. This is one that's at the Royal Tyrrell Museum that we've all had a chance to study in that lab group there. And what I realized really quickly, I always thought a paleontologist would be out digging trenches, uncovering fossils, beautifully articulated and already assembled, and very light layer of dust that you have to brush off. That's what the movies told me. It is a lot harder than that. But also I realized that if you wanted to be an academic in paleontology and study these things, there's another side to it that's really a lot of fun, which is you get to travel. Because in this case, the mosasaurs are found in museums all over the world, so I spent a lot of time during my master's degree in the backs of museums going through cabinets. But when the museum closes at the end of the day, you can explore. And so I got to go to all kinds of new places for a kid from Western Canada, and it really sort of opened my worldview to what's out there. But I did do work. So when the museums are open, you are working. And this is just some examples of some of the things I did back then, studying mosasaur skeletons in drawers and mounted to different things like this one here. And also a little bit of field work where we go out and find our own fossils to then bring back to the lab and prepare and study as well. So I got to do the paleontology thing. I got my first taste of it as a master's student, and then it was time to go on and become a doctor. Go get your PhD. And one of the best things I ever did was move. And what I mean by that is I had done 2 university degrees in my hometown. I had soaked up, the wisdom of all the people there and understood how they did things. And it's a really good thing in an academic career to move after a while and get a new worldview, get a new idea of how other people do this science and learn something new in the process. It was a really good thing for me from a personal growth perspective, but also academically. So I stayed in the same country on paper. I will say this though, Canada is very big. So I grew up up here in Edmonton, which is quite far north. I would guess it's about the same latitude as southern Scotland, I think. And I moved to the University of Toronto way over here, and that's almost the same latitude as Rome. So there was a climate difference even here. And it takes, 34 hours to drive that. And I did the maths one time. That's like something like traveling from here to somewhere in Western Kazakhstan, to give you an idea of how big Canada is. So it was a big move personally. And there I also decided I was no longer going to be an expert on a particular kind of animal, of a particular organism, and instead wanted to learn more about an organ and how it has evolved over the last 400 million years. And I wanted to look at that organ in a whole bunch of different extinct things to learn more about its ancient history. Of course, that organ is teeth, which I will get to, but these are some images of some of the kinds of animals that I got to study. So yes, there will be lots of dinosaurs in this talk. I did start to study dinosaurs. I don't actually consider myself to be a dinosaur expert, but they have teeth, so I like them. I studied a lot of ancient reptiles like this one here. They're even older than the dinosaurs, and this guy here called Dimetrodon, which is actually one of our distant relatives. It's more closely related to mammals. It's not a dinosaur. So if you see that in a toy box, you can know that that's not a dinosaur. There you go. And what I learned to do there was I became an expert in taking these fossils that someone has painstakingly dug out of the ground and prepared, and then I would cut them open with a diamond-edged saw. And I would grind them down on a microscope slide and make them super thin so that light could pass through them and study all the different parts inside. And these are called the dental tissues inside these teeth, and learn how they're different from ours, but also, and fundamentally, how they're the same as ours. What's changed and what's remained the same over tens, if not hundreds of millions of years, depending on the animal I was looking at. So this is some examples of some of the things I've cut, and I'll talk about a few of these in the talk. This is the process that I learned to do probably 1,000 times during my PhD. This is a little saw that we use. This is the sort of the head-on view of this saw. We embed our fossils in protective resin to stabilize them, and then you mount them which way you want to cut them. You glue them to a slide, and you cut it again, you grind it, and the next part's like an art. You have to learn how to grind it by hand down to just the right thickness, that enough light passes through that you can look at it on a microscope slide. So it takes a lot of practice, but it can be a very rewarding science. And the study of ancient tissues is called palaeohistology. Histology means study of tissues, paleo means ancient. Okay? So I'm kind of a paleohistologist now. And after I was done my PhD, I realized, okay, now it's time to really forge my own identity in this field and decide, try to get a job somewhere. And sell a university on the idea that I'm an expert on this one particular thing. I studied teeth. In that process, I moved back to my hometown for a couple of short-term contracts, these things called postdocs, and still got to do more paleontology work, more research, learning more things. And I started to wonder, where am I going to go with this expertise in teeth? And then I realized I needed to get a little bit creative. And I was starting to study not just fossils, but I was starting to study, along with my colleagues, the teeth of many living animals, because the techniques to study them are very similar. And sometimes people would recruit me onto their teams to learn more about something in their study animals. One of my favorites is we looked at the evolution of venom fangs in snakes. So we learned, because snakes, venomous snakes, when they bite, they inject venom through a syringe-like fang. And it's a very complex structure. And I was interested and my colleagues were interested in how that evolved from a simple-looking tooth. And so we did lots of work on that. We look at fish. We still look at fish in my lab. Fish fascinate me to no end. There was a lot of work on dinosaurs and many other things. But how do I turn that into something where I can have a future sort of as a professor one day in a university? Well, the opportunity, I realized, wasn't just in paleontology, but was to start communicating what I was doing to another discipline altogether, which to start talking to dentists and trying to get what I was doing out there to that crowd to help them understand that if we study the teeth of different animals, it's going to give context to why our teeth look the way they do and behave the way they do in health and in disease. And so we publish our work in academic journals. This is an example of one. This is not a paleontology field. This is actually a dentistry field here. Sometimes they think it's really fascinating. Sometimes they go, well, what is this? Why are you telling us about this? But probably the biggest opportunity I had was to speak at a dentistry event in my hometown while I was still there. In the Faculty of Dentistry, they did this theme, dinosaur dentistry. And someone realized, well, he's perfect for the job. We'll bring him to give a talk. And it's through that event, I can pinpoint a day where all of a sudden my trajectory changed. And it's because of that I ended up in London. So I won't bore you with the details of that. but in 2020, I joined King's College London on a short-term contract. I only thought I would be here for 2 years, and now they're stuck with me at King's College as a lecturer. And my official title is lecturer in Dental Biosciences, a fancy way of saying, I just tell people sometimes, I'm sort of like a dino dentist. Don't ask me to look at your teeth. I can't tell people, will not give you any medical advice or clinical advice. If you're a dinosaur, I can tell you something about your teeth, but that's about it. But I do work with a lot of dentists. And every time somebody meets me for the first time in that faculty, they ask me this question: why are you here? What does a paleontology and dentistry, what do they have in common? And it gives you a bit of imposter syndrome, because you go, yeah, what am I doing here? How did I end up here? But what I realized is I'm not the first to do this. And in fact, it's really, really important to the history of dentistry and to paleontology that people study teeth. Let me explain. In the early days of dentistry, particularly here in England, if you wanted to get a tooth pulled and someone to look at your teeth, does anyone know where you would go before dentists? Yeah. Yeah, you'd go to the barber. You go to the barber. So imagine that. Get your hair cut. After that's done, maybe they can look at something that's bugging you with your teeth. It wasn't a regulated profession, is what I'm getting at. It wasn't really a science-backed profession until people like this man, Sir Richard Owen, came along and started showing us the value of studying teeth professionally. Sir Richard Owen is a famous English anatomist, paleontologist, lover of teeth. And he wrote this book in 1840 called Odontography, with a much longer title I won't read out for you. And this book is really, really important. It's the first example in England of somebody grabbing the teeth of a whole bunch of different kinds of animals: fish, amphibians, reptiles, different mammals, human teeth, fossil teeth, modern ones, and he cut them open with a saw. He embedded them in resin, cut them open, turned them into microscope slides, and started describing what he was seeing. Sound familiar? Oh, my sense of belonging is coming all of a sudden. These are some of the illustrations from his book. The book is huge. I think it's like 700 pages. And these are some of the beautiful illustrations. These are sections looking inside the teeth of different animals. And when he did this, he realized that there was a pattern. No matter which tooth he looked at, he could see similar structures under the microscope. And he realized that teeth were fundamentally made of the same parts, and to those he gave names that dentists use every day. So this is the first time the word dentine appears. For you guys, this would be the inner part of your teeth that gives you your sensitivity to hot and cold. Thank you, dentine. He defines this tissue called cementum. I won't go into too much, but it's a tissue that dentists talk about all the time when treating teeth, just like the dentine. And he really championed this idea of comparing the teeth of different kinds of animals to learn something new. Now, the cool intertwining bit between dinosaurs and dentists comes from this, though. In this book, you see these things. These are teeth of two types of dinosaurs that were known at the times in 1840 from England. And I brought replicas of these. The one at the top, which I'll talk about in a bit more detail, is this one, which you can come up and see afterwards and handle. It's from an animal called iguanodon, a plant-eating dinosaur that has teeth that look like those of an iguana. And that's how it got its name, iguana tooth. And then we have this thing called megalosaurus. This is a lower jaw of megalosaurus right here, with this one pointy tooth sticking out. And I would give you one guess as to what that animal was eating. It's eating meat. But somehow, Richard Owen got a hold of some teeth and cut them open and made microscope slides. And there's the first microscope sections in this book from dinosaurs. Here's the weird bit, though. The word dinosaur does not appear in this book. Believe me, I've checked. It's not here. And the reason why it's not here is because the word dinosaur didn't exist yet. This is 1840, very early days in the study of dentistry, but also in paleontology, especially science of dinosaurs specifically. It wasn't until about a year or two later, after the publication of this book, that the word dinosaur is invented by a famous English anatomist, paleontologist, lover of teeth. And this man also founded the Natural History Museum over in South Kensington. So if you go there, that's partly his brainchild. And that man is Richard Owen. So it's actually the same guy who establishes the basic words that dentists use, as well as the basic words that paleontologists use. Dinos means fearfully great or terrible. Sauros or Sora, in this case, means lizard. And that's because Richard Owen at the time thought these were fossils of giant lizards. We know better now. We know that dinosaurs are on a different branch of the evolutionary tree of reptiles. Birds are living dinosaurs. The extinct ones with teeth are the ones we think of as dinosaurs traditionally, but they're not lizards. And I tell you that because Richard Owen was also a consultant on another little piece of London history, the first life-size reconstructions, or at least attempts, to bring these dinosaurs to life in what I like to call the Victorian Jurassic Park. And this is what scientists thought Iguanodon looked like at the time, and this over here is Megalosaurus with a me for scale in the foreground. These beautiful statues are still standing over in Bromley at Crystal Palace Park. Who here has gone there to see these? Who here now really wants to go see these after? Good, very good. You should definitely check it out. It's a beautiful place. So what I thought I would do now is, having given you that history, is another little bit that I realized out of pure coincidence is that through my own academic sort of upbringing, I've ended up studying very similar dinosaurs to Richard Owen. So I thought I would show you the things that we knew about them back then, and then show you some of the new things we're learning about studying dinosaur teeth using the same techniques now. And the first one I want to talk about is that Iguanodon. So Iguanodon at the time was known from only a few bones and a few teeth that looked superficially, so very similar to the teeth of iguanas. That's where it got its name. I got a couple of those here. I haven't studied Iguanodon specifically, but I have studied their close relatives that we call the duckbill or hadrosaur dinosaurs. And I'll show you lots of pictures of those in a minute. And their teeth are very similar. And we've learned a lot of really cool things about duckbill dinosaurs especially that I want to show you. This is an illustration of what a duckbill dinosaur might have looked like. They get their name because at the front of their mouth they have a beak almost that looks like the bill of a duck, duckbill dinosaur. That's used, we think, for cropping vegetation, which would then be ground down by all the teeth that they have in their mouth, and their teeth are spectacular. They have these things that look like one giant tooth in their mouth. This is a lower jaw. You're looking at the inside part of it. It's a right lower jaw. So the front of the mouth is over here. This giant brick looks like one giant tooth, but instead what these guys have is what's called a dental battery. It is a mass of teeth that are all coalesced together, all stuck together, that behave like one single tooth. I'm going to zoom in to show you this. This is a close-up. What I've highlighted here, this sort of diamond shape, that is one tooth. Like you and I, one tooth in our mouth. They stack up to 8 of these on top of each other, and they could be 20, 30 columns long in each battery in their mouth. And it acts like one giant tooth of these hundreds that are all stuck together. So it's developing new teeth. I mean, these guys would never need a dentist. They make new teeth all the time, and they grind away the old ones because they're grinding away at tough plant material. This is what the business end of a dental battery looks like. So this is the chewing surface right here, the grinding surface. It's grinding flat because of how hard they're grinding their teeth together to pulverize the plants that they then swallow. And if you look up close, you can see that there's different ones here that are different stages of wear. Some of them are very lightly worn, some of them are very heavily worn. They're just constantly making new ones at the bottom of the battery, and they're constantly moving up to the top, and they're grinding and grinding and grinding and grinding away. We've cut these open. My colleagues and I have been brave enough to try and cut them open. A microscope slide for one of these is about that big. It's not easy. But we've had a lot of luck, especially some of my colleagues, in cutting these open. And we've learned a lot of really interesting things in that process. So when we zoom in on one of these dental batteries, when we cut them open and look at them under a microscope, what we thought was a solid brick of hundreds of teeth all stuck together is actually a very dynamic, moving structure. One of the weirdest things that I didn't expect is that when we look at this, we see all these hundreds of teeth all together. Each one of these is one tooth. They're not actually physically touching each other when you look at them under the microscope. The thing that's holding these together, all the dark parts around these teeth, is actually mud and sandstone. And the reason why that's there is because when these animals died, all the soft parts that are around these animals decay, they dry and fall away. And if they're buried relatively quickly, then the sand and mud that they're buried under will get into all the little crevices. And that's what's happened here. So there would have actually been soft parts in between all of these teeth. And when we did the more detailed work, we realized there's a whole system of really complicated little ligaments holding every single one of these teeth together. We have those ligaments too. We have one set for each one of our teeth. So if you bite down like this and then you bite a little harder, you know how hard you're biting because the ligament is actually compressing a little bit. They have hundreds of those in their mouths. All of that moving too as they reach the top of the battery to grind away. The batteries are cool, but the individual teeth are also very cool. You and I, the enamel, the hardest part in our bodies, the hardest part of our teeth, the white part that you brush every day, on our teeth sits on top of our teeth. It's like a cap. In a hadrosaur, in a duck-billed dinosaur, they just have enamel on one face, one side of their teeth. And it's on one side of the teeth in the lower jaw, and it's on the opposite side of the teeth in the upper jaw. And when they grind together, that means that the hardest part, the enamel, is going to wear down the slowest, and the rest is going to wear down much faster. And what that does is it creates a continuously rough surface, because you have the enamel of all these different teeth popping up and wearing down a bit slower, and it keeps that surface rough to grind tough plants. I've become really fascinated by this. I've become really interested in enamel for lots of reasons, and I'm going to show you in a few other animals in a little bit. But their enamel itself is also really strange. When we look at that under the microscope, their enamel does some funny things when you look at it using special light filters. This particular filter on the microscope is telling us with light and dark patterns what the directions of all the little tiny crystals inside the enamel are doing. And I think you can tell right away, you can see these little wavy things, right? We have a very sophisticated sciencey name for this type of enamel. We call it wavy enamel. And the reason why it's doing that is because the crystals inside aren't going straight up and down like they normally should, but are instead spiraling like this. We've never seen this before in another animal, and we think that this is part of a crack-stopping mechanism, an adaptation that they have evolved because there's no single straight line through which cracks can go, and we think this is helping minimize large chunks of enamel coming off, although there's still lots of work to be done there. There we go. That's the plant-eating dinosaurs. Who here wants me to talk about the meat-eating dinosaurs? I'm looking at our younger members of the audience. Great. Okay, good. Well, I do a fair amount of work now on the meat-eating side of things as well, and there's lots of new things that we're learning from studying them too. And where Richard Owen studied animals like Megalosaurus, which I have the lower jaw of here, I've studied with my colleagues a lot of other different kinds of meat-eating dinosaurs, and I'll talk about those. And the meat-eating dinosaurs, the fancier sciencey name we give them are the theropods. Most of them are meat-eating, almost all of them, and so I'll use that name. We call them the theropods. And one of the things that's really fascinated me about them is something I can demonstrate here. So one time, I had to have a tooth pulled, my upper left molar, and I told my dentist, okay, it's got to go. I want you to pull it out in one big piece And he said, why do you want me to do that? And I said, because I want to cut it open and use it for presentations. And that's what I've been doing. So this is my tooth. And I cut it open, made a microscope slide out of it, and I, in this case, measured the thickness of the enamel on my upper left third molar, so my wisdom tooth. And I had about 2 millimeters of enamel on that tooth. Now, I want you to think about how big 2 millimeters is for a second. Enamel, that hard part we brush every day, the reason why we brush it is because it doesn't grow back. And so when we lose some of it, it's not going to come back. We need to take care of it. We have 2 millimeters of it. What about a dinosaur? What about a meat-eating dinosaur? This is one tooth of Tyrannosaurus rex from North America. It's about the size of a banana. That part is the part that would stick out of the gums. That's the business end, and this is the root that would stick in the jaw. Anyone want to guess how much enamel is on that tooth, the hard part that's gonna puncture into the food? How about this? Let's do a show of hands. Who thinks it'll have more than my tooth? Look how big this thing is. All right. Who thinks it's going to have less than my tooth? All right. Okay. Yeah, unsure, right? Well, a dinosaur tooth like this is going to have about 10% the amount of enamel that my tooth has. It is literally paper thin, maybe 1/5 of a millimeter. Super, super thin. And yet, these animals could crunch through bone and tear through meat with that enamel. So how does that work? They're doing so much with so little enamel. Here it is here. So this is our particular interest over the last several years has been in the cutting edges of the teeth of many meat-eating dinosaurs. T-Rex is a bit of an odd duck because its teeth are very round. Most meat-eating dinosaur teeth are very slender blades like this. And they have cutting edges on the fronts and backs, little bumps like these here, and they have a little tiny layer of enamel on the top, and these little bumps are like the serrations on a steak knife that they use to cut through meat. T-Rex has them too. You can feel them on the replica after. And what really got me wondering about this is, okay, they have like just a super tiny amount of enamel, but it must do something because it's there. Otherwise, they wouldn't have it. And I was really interested. Well, how does this work? How does this thin layer of enamel help those teeth function? And one of the things we started looking at was the structure of the enamel. And we're using high-powered microscopes, like this one here. This is called an electron microscope image, to look really, really high power at the crystals inside the enamel. And what we realized is that in a typical meat-eating dinosaur tooth like this one, if you image sort of anywhere off of the cutting edge, the enamel looks like this. So you have these little columns of tiny little crystals, and the little crystals are making little V's going up this way. But if you look at the enamel on the serrations, the enamel's doing something else. You're getting this spirally pattern to it, completely different from the rest. So clearly there's a difference in how the enamel is going to deal with cracking and failure. And when we look at it under a light microscope and we apply that filter, we see these little wavy patterns inside the serration enamel. We've seen that before, haven't we? Right? This serration enamel is built very similar to that of plant-eating dinosaurs that we think have that crack-stopping power to them. We're starting to look at that in more detail, try to understand. Like, there's actually a lot of complexity here in this tiny, thin little layer of enamel on these teeth. So really what a lot of meat-eating dinosaurs seem to be doing, especially the tyrannosaurs, so T-Rex and its smaller cousins, is they play around with the structure. So they're changing the crystals and the way they're organized around in the enamel on the serrated edge compared to on the rest of the tooth. And that's obviously the cutting edge is going to be really important. That's the part that's doing a lot of the work to help them feed. But what actually brought me to London wasn't just how the structure is changing, but we were curious, what about the chemistry? Because we know actually in nature, a lot of mammals especially, a lot of rodents, beavers, rats, mice, they play around with the chemistry of their enamel too to help make some parts of their teeth harder. And we were very interested in that. Maybe dinosaurs could do something like that too. And we haven't seen it yet. To address that, I had to come here and learn a whole new skill set. We get to play around at these big facilities here. For scale, these are cars down here. We go to these places called synchrotron facilities. These are giant, what are called particle accelerators, and they are shooting electrons around a giant ring at near the speed of light. And in doing this, release tremendous amounts of energy that we can use to study different things. The light that comes off of this facility into the different experimental parts in here is about 10 billion times brighter than that of the sun. That's the kind of energy that's coming off these things. We can use it to do different things, to look at fossil and modern teeth. This is us setting up an experiment during COVID times, so we're wearing our face masks. This is the person who actually convinced me, Owen Addison, to come to London. That's how we ended up here. This is my colleague, Alex Morel, who's been involved with a lot of this kind of stuff. And what the experiments look like is we make these are the teeth here. We make little tiny thin sections out of our different teeth we want to look at, and we blast them with the energy coming off of the beam here, and we're collecting information back here, but also right here about the chemistry of the teeth. And this is where things get a bit weird. We wanted to look at the serrations of dinosaurs, of tyrannosaurs, for example. So here's the serration enamel on 2 serrations. And I'm going to show you what are pictures of the different elements inside there. So this here is some of the elements we found inside tyrannosaur teeth. We found calcium, lots of calcium. Here's a weird one. The hotter colors tell us there's more stuff. There's a lot of zinc on the serration enamel. This one was our favorite. We're seeing a lot of tungsten. I thought, oh, better call New York Times. We have tungsten-tipped dinosaur teeth. How cool is that? But you might be wondering, how much of that was in those teeth when these animals were alive versus stuff that's been introduced in there because they've been buried under the ground for tens of millions of years, right? And we realized we shouldn't have started with the fossils. We should probably have looked at some modern reptiles first that have similar kinds of teeth to try and understand what elements we should expect to find there to figure this out. We need a good model. We need an animal that's alive today with teeth that are similar shapes to those of meat-eating dinosaurs. And we decided that our best model for this, and a paleontologist's best friend for this type of thing, is the Komodo dragon. This is where the dragon part of this, see, I told you I could fit all 3 of these from the title. This is where the dragon part of the story comes from. This is a skull of a Komodo dragon here. They can get to be about 3 meters long as adults, and they have rows of razor-sharp serrated teeth that are shaped almost exactly like those of a meat-eating dinosaur. And they're using to cut into the meat of their prey that we can study. This is what their serrations look like under the microscope, and we've cut them open, just like a tyrannosaur. They've got a thin little bit of enamel, and there's the little dentine bit underneath, under each bump on the cutting edge. So they're great. They look very, very similar. There's just one problem. Komodo dragons are from Indonesia. We're in London. This is a picture my friend took while she was on a trip to Indonesia to see wild Komodo dragons. And so I remember we were sitting in a coffee shop, my colleagues and I, one day, and where are we going to get Komodo dragons in London? Well, as it turns out, we had started thinking about this and started working on some museum pieces and things and started talking about this to other people. And I want to bring back to this picture I showed you at the beginning. I have to give huge credit to the London Zoo because they, unfortunately, lost one of their Komodo dragons a few years ago. He got very sick and had to be put down. His name was Gannis. He was a very beloved Komodo dragon at the zoo. The staff absolutely adored him. I think he's famous. He met Sir David Attenborough. I haven't met Sir David Attenborough. It'd be lovely to meet him. But unfortunately, he had passed away. And one of the staff at the zoo decided to contact us and say, hey, we've lost our Komodo dragon, but is there any way this could help with your research? And I said, absolutely. And so in here, I'm just shaking my head walking out of the London Zoo thinking, how did this happen? Just pure luck that this should happen. And we're learning lots and lots about him, about Gannis, the Komodo dragon, from that thing. Oop, of course I was going to push that button. Now, the cool thing about Gannis is when you look at a food's eye view in a Komodo dragon's mouth, which I don't recommend doing, These are his teeth looking top down onto his lower jaw. There's 4 of his teeth. One of them hasn't popped out of the gums yet. One of the things you notice right away is Ganas's teeth have an orange line on them, on the cutting edge of the teeth and along the tooth tips, every single one of them. A better way to view it is to use different types of light, which are going to cause the teeth to glow, except for parts that are made of different materials. And when we do that, it pops out even more. Every single one of Ganas's teeth, as they come out into the mouth, have this one line along the cutting edge, on the trailing edge, and the leading edge. What is it? I'm very curious. I'd never seen this before. So I went to museum collections, and with my colleagues from around the world, looking at Komodo dragon skulls in the collections, and we realized every single one of them does this. It's like someone took a little paintbrush with some orange and just carefully dusted the cutting edges that orange color. Well, it was back to the synchrotron. That's going to tell us what elements are inside there. And so what I'm showing you here are a couple of serrations from a Komodo dragon tooth. This is an elemental map of calcium. That's the enamel right there. It shines like brighter with calcium signal because there's lots of calcium in our enamel, so it makes it so hard. This is zinc. Sometimes we get some funny things with zinc. We're wondering if that might be part of it because we saw it in dinosaurs, but the one that really stuck out was iron. This is the elemental map of iron. And when we put the 3 together, we realize the iron is just along the outer edge of the enamel on the serrations. But is it just on the serrations? Is that iron found everywhere on the tooth? Because if it is, that won't explain the orange color. So we cut the teeth this way. Now we have the trailing cutting edge of the tooth and the leading cutting edge of the tooth in this view. And the iron map looks like this. So it concentrates on the cutting edges of their teeth on the fronts and backs. They're actually sequestering or concentrating that iron onto those specific parts. That's the part that is giving those cutting edges the orange. They're putting iron into their teeth. And when we look at them under the high-powered microscopes, like an electron microscope, the enamel is very thin in a Komodo dragon. You thought T-Rex enamel was thin. A Komodo dragon's enamel is probably about 10% the thickness of a dinosaur's enamel. Super, super thin. But on top of that, you have this almost like porcelain-like coating on the serrations that you see under the electron microscope. Super thin. And we can do elemental maps and study its chemistry at that magnification too. This is 2 serrations. This is the calcium signal that's in the enamel. And we can overlay on top of that the iron signal. And the iron signal is exactly where that coating is. So it's not just that they're concentrating iron into their enamel on the cutting edges, it's a physical coating that they've developed on top of the enamel that's helping keep those serrations sharp and last just long enough to cut through whatever they need before that tooth will be shed and a new one will take its place. So it's a completely different adaptation from what we've seen in the tyrannosaurs. Instead of playing with the structure of the enamel, they play with the chemistry, and they put these coatings on their teeth. It was a lot of fun doing this work. Lots of people were involved with this from the London Zoo, from different universities. My favorite part about this is because Komodo dragons are so iconic. Nature documentaries have done the work for us. The media loved it. They've talked about this all over the place, and we got to tell this story to as many people as we could possibly reach. But that's not where the story ends. Ganas is still teaching us new and interesting things, unexpected things about Komodo dragons. And we've taken Ganas to the dentist. We've taken him and given him what's called a CBCT scan. So this is, if you were to sit there and the scanner would go around and take X-ray images of your teeth, we've done that with Ganas, and we can create a 3D model of what's inside Ganas's mouth. The teeth in blue are the ones that were sticking out of Ganas's gums the day he died. The teeth in green are the ones developing inside the gums. These guys are tooth factories. They're constantly making new teeth throughout their lives. For every 1 tooth sticking out of the mouth, there are 4 underneath it developing at different stages. So that's great because it's giving us a freeze frame shot of how they put the iron and when they put the iron on their teeth. And as it turns out, even in the tiniest little buds of developing teeth, we can see the orange glow beneath all the soft tissues of the iron layer. And they add it super early in development, which is quite cool. So it's built in to every single Komodo dragon tooth that they have this iron coating. the lesson I learned is I thought I understood these animals pretty well based on work I had done before. But what I love about this field is you are constantly being surprised. And so even though the Komodo dragon is a paleontologist's best friend because the teeth look very similar, they actually can do completely different things with their teeth to achieve the same outcome. Now, to end, I like to think that we get dentists really engaged and enthused about teeth and teach them new things they didn't know about teeth all the time. That's great. But how else can our discipline of studying teeth of different animals help the broader community? And this is something that's pretty near and dear to my heart. I try to do a lot of this whenever I can, like being here today. Because the replicas I brought, and I really encourage you to come see them, these are specifically ones that we've bought for outreach programs that we run out of our little natural history museum over at Guy's campus, King's College London. We have a little museum called the Museum of Life Sciences. They have an open day coming, I think, this summer. And is it in August, the open days? I can't remember. But we put all these things out. It's a beautiful little place. And out of there is our home base to train dentistry undergraduate students to teach about oral health care and about tooth anatomy and about careers in science and technology, engineering, and medicine, not with human teeth, but with dinosaur teeth. And for the kids in the audience, how much more interesting would that be? Yeah. So we do go to schools, and schools sometimes come to us for different events, and we run these programs. The undergraduate students, the dentistry students, really enjoy doing this. They get out in the community, they meet people, especially we've been doing a lot of it in Southeast England with our widening participation teams, to go out there and just engage with kids, especially around year 6, year 8, although we have programs for older children, to just teach them about teeth and how fascinating they are. Maybe that'll inspire dentists, maybe it'll inspire paleontologists. And we love doing it. We get a lot of attention for doing this, but really our goal is to get kids in and put them face to face with some of these amazing types of animals. We also do student surveys, and that is my favorite part, because when you survey a year 6 student about what they thought about looking at dinosaurs for an afternoon, you get the best reactions. Was there anything you didn't like about the workshop today? It ended. Sad face. Now here's the crazy bit that I had to look twice before I realized that sad face is drawn like they would text. Huh, yeah. I like this one. Was there anything you didn't like about the workshop today? No, like this. Beautiful. And then the ones that for us, sometimes, but they bring a bit of a tear to your eye, especially for our dentist volunteers. What do you want to do when you grow up? I want to be a dentist. What did you like most about the session today? I learned that I want to be a dentist. So to end, it's been a journey so far. It's nowhere near the end for the journey for me. I'm going to keep going and doing these things. It's been a transformation from what I originally thought I would do as a kid, from studying dinosaurs and digging them up in the field. All of a sudden I'm studying mosasaurs and then teeth, and then I'm in dentistry. But I will say, I feel like I'm back here again. I feel like you never lose that childhood fascination when you get to work with animals like that every day. And so I would say this, it's a tough road to get to that stage, but it's also a labor of love, and so it's never really work. It's something we really enjoy doing. I need to thank a lot of people, and thank you for paying attention, and I hope I'm not too over time, but a lot of people that have helped sort of with a lot of the projects that I've presented today, a lot of support and assistance, a lot of funding, and the synchrotron facilities that help do this. I didn't have time to talk about crocodiles of the world. We study crocodiles too, of course, and they've been amazing for helping us with that. Of course, the London Zoo as well, and thank you for listening.
Okay, so I have a question. This is about meat-eating dinosaurs.
Sure.
But is there any interesting variation in enamel content between different meat-eating dinosaurs rather than just a T-Rex?
Yep, so we are, the fun thing about the study I showed you is, of course we picked tyrannosaurs to study first. Why wouldn't you? But that doesn't mean that that's the only adaptation that we're going to identify. So more in depth now, we want to understand how the teeth of much smaller meat-eating dinosaurs worked when they're on the same scale as something like a Komodo dragon. Is that where we're going to start to see them playing with the chemistry of their teeth? And that's something we don't know yet, but we're actively looking into. So for Velociraptor fans out there, they're on our hit list, as well as their relatives. Yeah.
Thank you.
Mm-hmm.
Thank you for your talk. That was very insightful. I just have a question about how maybe if there are any insights that you've gained from studying fossil teeth and how they've maybe been underutilized in modern dentistry. So some methods that you think maybe aren't as investigated.
Sure. Yeah. So what kind of insights could we gain from studying fossils for dentistry? One of the big things that we're focusing on now is I've shown you these pictures of these different kinds of enamel in these different dinosaurs. Those are types of enamel that don't exist today. And what's cool about them is they're playing around with structures that are a lot simpler than the enamel structure in our mouths. And there's so much research that goes into, in dentistry, and trying to find ways to artificially grow enamel, because that's the part that doesn't grow back. That's why dentistry really exists. And we're not getting past even the start line, really, to reconstruct the complexity of our own enamel. And so one of our arguments is, why don't we look to nature for much simpler design solutions, so to speak, to try and artificially grow simpler types of enamel that accomplish more or less the same thing. That's our pitch to how that could be important. Yeah.
Thank you so much for the talk. I just had a question on, you told us about all these amazing places that your work has taken you all across the world, and I was just wondering what you thought was the most interesting place you've seen.
Ooh, yeah, that's a good one. The most interesting place I've seen. Yeah, that's tough. I would say going into Argentina, into Patagonia, was pretty amazing, seeing the kinds of fossils are out there. It was a desert, a high altitude desert. It was a really interesting place. I got to see baby rheas running around, these flightless birds. The babies are this tall, running around. Thorns that were that long from plants that, you know, the thorns were this big. I still have one stuck in my hiking boot that I can't get out. They pop your tires. They're like steel. Just the environment was just totally different from what I was used to, and I absolutely adored it. Yeah. Still in my boot. I can't get that.
So following on from that, if you had to save one site where we know there are fossils, what site would you save?
What site would I save? Oh yeah, that's a tough one. I mean, I'm partial to the sites in Alberta, in southern Alberta. They're really, really important for understanding the ecology of dinosaurs and other extinct things, because there's just so much of it. Saving that, I think, would be priority for me, but that's also me being partial to being an Alberta kid. But yes, definitely that. Yeah.
One more question, if I may. The tungsten in the tooth.
Yeah.
Was that something that was laid down later? Or
it was laid down later. We're pretty sure. We can't. So if it was something that you saw across every single tooth every time, then you'd start to be suspicious, and then you'd investigate that in more detail. But we don't see that consistently. And the other thing is you find all kinds of weird elements in fossil teeth, depending on where they come from. So we've had elements like yttrium and chromium. I forget what other things we've had in there, and it's just unusual stuff that's clearly come in after the fact. I mean, those teeth have been buried underground for 70+ million years. There's going to be all kinds of things that get in there over time. But yeah, we're trying now to figure out how to rewind the clock, eliminate all these things that are from it becoming a fossil, and tell what the chemistry looked like when they were alive. Yep. I think this is going to be a tough question. The younger they are, the tougher the question.
Did Komodo dragons have the wavy serrations too?
Great question. Did the Komodo dragons have the wavy serration, like a wavy enamel like a dinosaur? No, they didn't. The enamel is super thin, and the crystals all just go straight up and down, like this. Very, very simple. It's like the simplest way to build enamel. And so we're kind of confused. Like why would one animal change the structure and the other one change the chemistry? And one of the ideas we have is it's a matter of scale, right? So a Komodo dragon, even though the enamel's thin in both of them compared to you and I mean, a Komodo dragon's teeth are that big. T-Rex's tooth is that big. And so even though the enamel's thin, there's 10 times more of it here, and there's a very, very small amount there. And so you have enough room here to change the structure and have it actually do something. Whereas here, it's not going to do much. And so instead, we think they add on the iron coating. And that's what they use to cut through. Yeah, yeah. Their teeth are razor sharp, by the way. Razor sharp.
Hi, I have a question about the bumps on the cutting surfaces. Are they anything to do with the way that the enamel's formed? Like, do they start at the bumps?
Yeah, so how do they make the bumps? We're actually using Gannus, the Komodo dragon, to understand that. Because now we've got all these teeth inside the gums that are at different stages of forming. So we are, even today, doing that in the lab, in my lab. Our students are working on that, yeah.
Because in human teeth, they seem a bit like mammals.
Yeah, and you get, they start at the cusps too in human teeth. We're very curious what they do in these guys. And Komodo dragons are the best model that's still alive today to understand that. They're not the only lizards with serrated teeth, but they're certainly the largest, and so the most obvious and easy to look at with the techniques we're using. Yep.
You talked at the beginning about discovering a new species of dinosaur, which must have been completely thrilling.
That was cool.
And naming it.
Yep.
I just wanted to know what the rules are. Could you call it whatever you want? Who decides whether it's allowable or not?
Number one rule, you can't name it after yourself. So when you see lots of species are named after people, but it's not the person who found it or discovered it that gets their name attached to it unless somebody else comes around and names it after them. That's rule number one. The other rule is you're using typically Latin words, Latin-rooted words, because it's, you hear that term all the time, it's a dead language. What that means is we're not seeing it change, the language change and evolve, and the meanings of things change over time. And so we can use Latin words to describe a species, and I could speak to someone in Spain, in France, in China, and they would know exactly which animal I'm talking about. So Tyrannosaurus rex, that means tyrant king, right? Allosaurus means, I think it's jumping lizard. Dinosaur is not an English word. Dinos means terrible or fearfully great. Sauros means lizard because they thought they were lizards. They were wrong, and so the word dinosaur is actually the wrong word we should have used to describe these animals, but we're stuck with it. That's the other rule. As long as there's no other egregious rule breaking, the name is stuck, and you can't change it. And that's why we call them dinosaurs. Yeah.
Why did you call yours?
Oh, yeah. So this was a mosasaur, this giant marine lizard. Aremiosaurus heterodontus. So Aremiosaurus means the sand lizard, because it's from what is now dry desert. And heterodontus means different shaped teeth, because one of the defining features of that animal has very different shaped teeth at the front of the mouth compared to the middle of the mouth compared to the back of the mouth. And that's what I decided to do with it, yeah. So I couldn't call it Aaronsaurus LeBlanci or anything like that, yeah.
I was just wondering, when did teeth evolve, and did they evolve more than once, and did we get it right first time?
Oh, yeah. I don't know the second question, did they evolve just once? And people are fascinated by that question. When did they evolve? The oldest teeth that we can all agree that come from the mouth, I'll get to that, are from about 439 million years ago, I think, give or take a week. So they're from China, the oldest ones described. We know their teeth for reasons I won't get into, but the challenge when you go far enough back in time with the origins of teeth is that there's actually lots of different organs that look like teeth that are not found in the mouth. To give you an example, anyone here ever touched shark skin? So it's really, really smooth going one way and then super rough going the other. That's because sharks basically are covered in microscopic teeth. So if you cut them open and look at them under the microscope slide, they're made of the same parts as a tooth. And so when you go far enough back, you find a little tiny speck and it's got all the parts that you think are from a tooth. Could be from a scale on the body of a fish. Yeah, that's the challenge. But new discoveries challenge that all the time.
Is there a particular dinosaur tooth that you would pick? That's your favourite?
Oh, that's another hard question. Okay. My favorite dinosaur tooth. So normally I would try to be a little bit contrarian, we will say, and say I don't like meat-eating dinosaur teeth because they all look the same. But now I've proven myself wrong. One of the things I didn't talk about with meat-eating dinosaur teeth that I think is really cool is in between each serration, there's actually a little purpose, I wouldn't call it purpose-made, that's evolved, but they have a little channel in between each serration and a little hole inside the dentine. It's a perfect crack-stopping feature between every single serration. That is really cool. They've developed something that sophisticated. So I will give them the benefit of the doubt. I'll say the meat-eating dinosaur teeth are my favorite now, but it changes every few years. Yeah. Good question.
Hi. Why do you think that the way humans have evolved is that we only get 2 sets of teeth? Because that seems like a bit of an evolutionary disadvantage.
Don't tell the dentist that. Yeah, why do we only have 1 set of adult teeth? So that's not a human problem. It's a mammal problem. So your dog, your cat, your hamster, your lab rat, take your pick, they all have that limitation. They can only make 2 sets of teeth. They can make their milk teeth, and then they can make their adult teeth, and that's it. And we have to take care of those. That feature, the ability to constantly make new teeth, we lost. We lost it probably over 200 million years ago. I showed you that thing with a sail on its back that walked on all fours, Dimetrodon. It's a distant relative of us. Back then, they could make new teeth all the time, no problem. And so there's lots of people wondering that exact thing. Why did we lose the ability to do that? Some people think it coincides with when we start to chew. So if you're constantly shedding old teeth, you're going to have a little gap in your smile quite often. And if your other tooth has nothing to chew against, it becomes pretty much useless until that other one comes in. And so some people think that's when animals that didn't replace their teeth as often would be more successful, they'd feed more, have more young, pass on the genes for more limited replacement of their teeth. That's one of the ideas out there. Yeah. Impress your dentist next time you're in the chair. Yeah.
Anyone just have any questions or online? Do we have any? Okay, perfect. Thank you so much. That was so insightful.
Please come up and check out the gas.